Hi, this is chapter 10 on organohalides. Of course, we know an organohalide, any organic molecule, we're a halogen atom. So we'll be talking about fluorine, chlorine, bromine, and iodine bonded to a carbon, and all the interesting properties that come from having that bonding pattern. We'll be using X all throughout this chapter in this course to refer to any of the halogens. So just as an abbreviation. So these organohalides, they're very useful as compounds in synthesis, as we'll see. We'll be able to modify whether the carbon is a nucleophile or an electrophile if I have an organohalide. Some compounds are just very useful on their own. Take a look at trichloroethylene. This is used as a solvent in dry cleaning, for instance. If you have something to be dry cleaned, that's one of the solvents that's used sometimes because it can be very easily evaporated and recovered. Halothane, or most inhaled anesthetics, have some manner of fluorines, chlorines, or bromines attached to small organic molecules in several different combinations. Refrigerants, right? Dichlorodifluoromethane, CFCs, right? Chlorofluorocarbons are an entire class of compounds that have chlorine and fluorine attached to them. Something else that's not listed here, halogenated polymers, especially fluorinated polymers, like things like Teflon. CF2, CF2, repeated indefinitely. That's Teflon. Companies like 3M have made entire industries out of fluorinated chemicals. So 3M Scotchgard is a fluorinated chemical, for instance. And especially those fluorinated chemicals, you hear about those an awful lot in the news. They have attractive chemical properties in that things like Teflon, it's very difficult to get something to stick to it. Scotchgard, stains won't stick to it. So favorable chemical properties, but some not so favorable environmental properties, because since they're so stable, they tend to collect up in groundwater and landfills and don't degrade so much on their own. 3M has gotten into quite a bit of trouble recently over some contamination of fluorinated compounds that's been leaked into the groundwater around their former factory locations. So let's just get our classifications down here. Vinyl halide, aryl halide, and alkyl halide. Vinyl halide has the halogen bonded to a CC double bond. So if we look at our trichloroethylene here, we've got chlorine attached directly to a CC double bond, right? Or to a carbon that's been double bonded. That's called a vinyl halide. Anything vinyl is when we've got something attached to a carbon-carbon double bond. So aryl halides have halogen bonded to a benzene ring. So if I have a benzene ring, remember 6 carbons alternating single and double bonds, and something like that with a bromine attached. That's bromobenzene. Bromobenzene is an aryl halide. Alkyl halides, we have X bonded to an sp3 carbon. So carbon with 4 bonds total, carbon that's single bonded to everything. If we have an X, if we have any kind of halogen attached to it, that's an alkyl halide. And that's what we will be talking the most about in this chapter, alkyl halides. But halothane up here, this 3 fluorines on one carbon, a bromine, a chlorine on the other carbon with the H. So that's just an alkyl halide. We already know pretty much how to do nomenclature of alkyl halides. It's just the normal IUPAC rules. We use fluoro, chloro, bromo, or iodo as substituents in the name of the compound, and we just number those with any other substituents alphabetically. So if we take a look at our example compound here, I've got a double bond and a triple bond, a chain of carbons. The longest chain has to have the double and the triple bond in it, if at all possible. Number from the end closer to the double or triple bond. So 1 is where the double bond is, 3 is where the triple bond is. I have a chlorine attached to 1. I have a methyl on 2. I have a bromine on 5. So the substituents, at least, will be 5-bromo. All right, we'll start with B alphabetically. 1-chloro. Then what? Methyl, M. 2-methyl, 5 carbons, 2-methyl pent, 1-ene, 1-en, 3-ine. That's what those new IUPAC names, which remember, I think those are easier when you have mixtures of single and double bonds. Because if you wanted to use the old IPAC, it would be 1-pentene, 3-ine. We're forgetting one thing, though. This is a tri-substituted double bond. So chlorine and H on one carbon, chlorine has priority. Methyl and triple bonded C on the other carbon, so the triple bonded C has the higher priority. Those groups are opposite each other, so E apart. So let's put in parentheses 1E before the start of the name. 1E, 5-bromo, 1-chloro, 2-methyl, pent, 1-ene, 3-ine. That's the name of that compound. So we already know how to do that. We hopefully should have been able to do that before this chapter. Just good to review it, though. I have 1-carbon compounds down here with 1, 2, 3, and 4 chlorines on them. And I write these down here because alkyl halides like this, simple ones that are just a methyl with varying chlorines, are widely known by their common names. So let's do IUPAC for each of those, and common names. All right, let's start with IUPAC. So CH3Cl, chloromethane. No need to call it 1-chloro, of course. CH2Cl2, dichloromethane. We've used dichloromethane quite a bit. It's a fantastic solvent to be used in organic chemistry. It dissolves pretty much any organic compound. And the neat thing is it's denser than water. So if you want to do an extraction, if you want to get your compound out of the aqueous layer, you add some dichloromethane and shake it up. Your compound will have moved into the dichloromethane layer, which will be at the bottom of the separatory funnel. So you just drain that off and add more dichloromethane. Shake it up, that's at the bottom, you drain it off. You can do that as many times as you want. You never have to pour it out of the top again if the solvent is heavier than water. So that's very useful. I think that's one of the reasons it's such a popular solvent for organic chemistry, because you can do real easy extractions with it. So dichloromethane, trichloromethane, tetrachloromethane. We'll just use some ditto marks there to show you. You get the idea, though. Chloromethane, dichloro, trichloro, tetra. Okay. So common names work a little differently. The common names for alkyl halides are sort of named like an ionic compound, even though there's no ions here, of course. The nomenclature style for ionic compounds is, things like sodium chloride, calcium oxide, right? So if I, instead of calling this chloromethane, if I call this some sort of chloride, it's methyl chloride. We just use whatever kind of R group it is with chloride. CH2Cl2, it's still a chloride, but instead of CH3, which is a methyl group, a CH2 group is called a methylene group. A secondary carbon that has 2 hydrogens on it, that's a methylene. Methyls are primary. So this is called methylene chloride. So I've tried to encourage us to use the IUPAC names for common substances like this. So dichloromethane is really what it's commonly known as in industry. If we want to call it DCM, that's a common abbreviation for it. But in the past 50 years or so, that compound has been very commonly known as methylene chloride. So it might even be called methylene chloride in your textbook, but I've gotten used to calling it dichloromethane. So methylene chloride, CHCl3, has a common name that is not related to its structure. One of those things that was the name was known before its structure was. So CHCl3, we called it trichloromethane before. It's also known as chloroform. So something that'll knock you unconscious if you get too much of a whiff of it, and they had used that for anesthesia previously, along with ethers and things like that. But that's chloroform. CCl4, tetrachloromethane. If I go back to calling things by chlorides, this is called carbon tetrachloride. That's back to sort of inorganic molecular nomenclature, carbon dioxide, phosphorus pentabromide, things like that. So carbon tetrachloride is a common name, where IUPAC for organic nomenclature would call that tetrachloromethane. So carbon tetrachloride is different from all of these because it is nonpolar. All the other ones are polar to some extent, dichloromethane being a very commonly used polar solvent, but carbon tetrachloride is non-polar, so it will not really dissolve polar compounds very well, but it'll do great on non-polar things like alkanes, hydrocarbons, stuff like that will dissolve oils, greases, things like that in carbon tetrachloride.